Hello there. This is my submission for project number 1 in Fluent for Fluid Mechanics Summer 2025. Today I'll be modeling the combined Poussielle and Coullette flow. The individual Poussielle and Coullette flow is in the other video conducted by my partner Jesse Jotner. So see that for our other submission. So now that we have Workbench open, we can get started by pulling in a fluid flow Fluent from the toolbox into our project schematic. We're going to left click on geometry to open up the properties container and change our analysis type to 2D. Now that we have that, we can right click geometry and select new design model or geometry. So we get started by modeling our geometry for our analysis. Now that design modeler is opened, we can select our Z plane. So we get a 2D view, so we can start modeling. We're going to select sketching up to rectangle. I'm going to start our rectangle at the origin just to make the model easier. You can click and drag out and click again to create our rectangle. The rectangle is created. We want to create some dimensions. We're going to use the general dimensions and select this upper side of the rectangle and then the vertical side of the rectangle. These are in meters, but we want it in millimeters, so we can go up to units and select the millimeter. We're going to make our length 1500 and our height, and our height 10 millimeters. We can zoom in and look at our rectangle we just created. We're going to go back to modeling and select concept, surface from sketches, and then change our select option to box select so I can select all these at the same time. Click apply and generate. So now we have one full surface which we can create a mesh for. So we're going to go back to workbench, double click mesh, and wait for the mesh modeling software to open. Okay, so our mesh modeling software is now open and it is loaded in the geometry we just created. So we're going to want to start by creating some name sections, which we can change our select mode to edge. Go down to this upper wall. We're going to left click that and then right click and select create name section. We're going to name this upper boundary. And then we can do the same thing with our lower boundary. As well as our inlet and outlet. Okay, so we can expand our name sections to make sure everything is correct. You see all the green check marks. So we did that step correctly. So next we can start our mesh. We're going to select mesh, opens up the meshing toolbar. We're going to do some sizing meshes. So we can select our upper wall and our lower wall. Go over to geometry and select apply. We're going to change our type to number of divisions. And we can do 2500 divisions. I'm going to turn captured curvature to no and our behavior to hard. And we can select generate. Just going to wait for the mesh to generate and then we can continue meshing our geometry. Okay, so now that our first mesh is done, we can go back to mesh See that we've created a preliminary mesh. We're going to create another sizing mesh, selecting our inlet and our outlet, selecting apply, and then similar settings here, number of divisions. We're going to use 80 divisions for the height, turn capture curvature to no, and then our behavior to hard, and we can generate this mesh. Alright, so our second edge sizing is done. Select mesh again. You can see that our mesh is a little bit more defined. So we're going to do a face mesh just to cap things off, make it sure it's super well organized. We can select the face, select apply, and we're going to keep all these settings, and then select generate. Okay, now that our meshes are done, we can select mesh and just verify that it's very uniform and looks good, which it does. And we can go back to workbench and update our mesh by right-clicking and selecting update. Now that we have a little check mark next to mesh, we can double-click setup and wait for the setup window to load. I'm going to keep all the default settings and select start. Wait for the Fluent window to open. Okay, now that our mesh and geometry have uploaded into Fluent, we can start by changing our flow by opening up the models in this setup section, and we're going to change it from viscous to laminar flow, or a laminar model. We can then go to results and residuals to change our residuals. I'm going to do 1e to the negative 0.6, but this can be any value which you choose. Select OK. You can close this down. We're next going to want to change the properties for our fluid, our density and viscosity. So our density for the setup is going to be 998.2 kilograms per meter squared, and our viscosity is going to be 0.009 kilograms per meter seconds. We're going to select change and create. Close this window down. We're next going to go to our reference values. We're going to do compute from the inlet, and our reference zone is going to be the surface body. And then we want to verify that our density and viscosity, which we changed prior, is updated, which it appears to be so. So that is all good. We next go to our boundary conditions. Because this is a combined Poussielle and Coullette flow, we want a inlet velocity as well as a moving upper wall, which we're going to change in a few seconds. But our velocity for the inlet, we're going to select as 0.6. Hit apply and close. Don't need to adjust the internal. For the outlet, the other thing we're going to change is to make sure that our flow does not reverse. So we're going to select this checkbox to prevent reverse flow. Select apply and close that. And then for our walls, our lower boundary, we want to remain stationary and in the no slip condition, which it is. So we can select apply and close that window. And then for our upper boundary, we also want the no slip condition, but we want the wall to be moving to represent that Coullette flow of the combined flow. Our upper walls will be moving with a velocity of 0.4 meters per second. So we can input that and select apply and close this window down. I think we should be good to move on. Let me just make sure that everything uploaded correctly. Check our outlet, lower boundary, and our upper boundary. Those all look good. We can check our reference values one more time. All good there. So we can move to initialization. Select initialize and wait for that to run. Now that the initialization is done, we can run our calculation. I'm going to do 350 iterations. Should take a little bit longer, but it should get a more accurate model. We could do that and select calculate and wait for our residuals to load. Gonna wait for this to run through our iterations. Should take a little bit of time, but not too long. And hopefully we get some convergence of our x and y velocity. Okay, now that our calculation has completed, you can see that we got rather good convergence. It should be okay for our model. So we can move on and go back to our workbench. Let's take another look at this to make sure this processes. Go back to our workbench and we can select results and double click that. We want to select the z-axis so we can view our model as we model it. Then we're going to want to create a few lines along our model so we can analyze at those points. So we want to select location and line. Our first line is going to be our midline because our model is 1500 millimeters long. We want it to be half of that, so we're going to do set 0.750. So we'll also be 750. And then it's 10 millimeters high, so we're going to do 0.01. And we can adjust our samples to 100 and select apply. You can see our first line there. And we're going to repeat this 2 more times for our developing region. We're going to put our developing region at 0.01. Sorry, 0.1. And the height will be the same, 0.01. And our samples will be 100, and we can select apply. Oops. Like that. There we go. Adjusted. So this is our developing line. And then we can do our end line, which we're going to put just before the end so we don't do any calculation errors. 0.499 and the height. And our samples again at 100. You can see our third line. So next we can create our contour by selecting contour. Just accept the default name. For our location we want symmetry 1. And then for our variable we want velocity u. And then we can do 110 contours and select apply. For this to load in, so that looks good. We're going to move our legend just above so we can see this. We can by selecting default legend view, or double clicking that and selecting horizontal and apply. We can zoom in on our contour just to take a look at it, see how it's doing. Looks pretty good. We have our boundary layers developing, and eventually somewhere down the line we have a fully developed flow. Next we want to go to chart viewer, and we're going to create a view so we can see our velocity profiles. So we're going to go up to chart, select chart, accept the default name, and we're going to name this combined flow. And we can select our data series. We're going to do each of the lines we previously created. So our end line, select our location as the end line, create a new series, and do our midline. We can select our midline and then create our final series as our developing region, and select developing region. And then for our x-axis, we want this to represent our velocity u, and then our y-axis is just going to be the y height. And we can select apply. Alright, so here is our velocity profiles for our analysis. On this graph, we can see our midline in the blue as our fully developed line, and our developed region is less because it's not the velocities are still varying along the x and not just in the y direction. So we are going to, you notice that our end line is not visible, but that's because our end line and midline are roughly the same because our flow develops rather early in our pipe. But I can just go and select, deselect our midline, so you can see the end line there. It's just directly under our midline. I'm going to reselect that. And then for more of the analysis portion, collecting our data, we're going to want to export this graph as a CSV file. I'm going to put it in my download so I have access to it, and just name it combined flow 2.1 and save that. This is the wrong file. Then we can open up this file, the Excel file, and determine our maximum velocity and at what point, what y value it does. We're going to convert this. Except this. We can select our end line or our midline because they are about the same. Since select the end line might be a little bit more accurate. Then we can go to select any cell in the Excel file, go to formulas, go to maximum, and then we can select this section of the velocity for the end line. Should be about 100 values in here. And this will return our maximum value in those cells, which appears to be 8.16. The negative 0.1, so we can find that in here. Let's see, 8.15, 8.16, 64, 60. So this one appears to be our maximum velocity, to be 0.81 meters per second. And then our corresponding y location is this one, located in the formula bar. Convert that to millimeters. 5 millimeters, 5.8 millimeters. So just above our midway point, which is to expect because our flow is not symmetrical because of the upper plate that is moving. Alright, so we can go back to here, and that should be all we need for this analysis. So thank you for watching. Please reference the other video for the Poussielle and Coullette flow that are modeled individually. Thank you.